and then HI. That is equal to the rate times volume for a CSTR, right? And so what you end up with then is temperature times U one more row before we put down the final one. So what is Q for a CSTR? Q is just U times A, TA minus T. It's the same. The only difference is now this is going to be treated typically as constant for a jacketed around a CSTR. The temperature is also constant, and so it's just simpler to work with. You don't have to worry about the differential form.
Why is temperature constant?
The CSTR.
So in the PFR expression for dQ over dV, that temperature is not constant.
No.
Okay.
Right. It's changing along the volume of the reactor. Yeah.
So is that because the inlet's giving out temperature and outlet's giving out temperature, but the reactor's at a constant temperature? It's steady state.
Okay, a CSTR operates at one condition, one temperature, one concentration. The outlet temperature is the same as the temperature of the CSTR itself, but the inlet temperature can be different, right? It's a pipe. It can be at whatever damn temperature you want. It's going to drop into this bath that's at a specified temperature. But yeah, that's why you can still have a quote-unquote non-isothermal CSTR, even though it's all at one temperature. The inlets are at a different temperature. All right, so where was I? So this change in enthalpy, right, without phase change, and if we assume that we have a temperature-independent specific heat, then that change in enthalpy becomes the heat capacity times the change in temperature. And then we keep going. What is this again? Delta H reaction. No, because I'm.
Oh no, to the left of that expression. Because you're just converting it.
No, I swapped the
Oh, you
temperatures.
swapped the T's. Oh, okay.
And then here again, it becomes a plus because the negative ends up inside the delta H of reaction. That's how the book always does it. They always have negative delta H of reaction. So then times negative RA V, that's what this is for a CSTR. That is equal to that. And then again, you're setting it equal to 0. So this is the expression for a PFR. Here's going to be the expression for a CSTR. It's not a differential equation. Okay, any questions? So it might look in many ways similar to what we had before, except now, of course, we have a term here, which is representing the Q, the fact that it's non-adiabatic. And I mean, that term ends up in part of your denominator as well, once you rearrange to solve for temperature. Yes?
Should we not have minus T and T minus T? You didn't actually get T out of that.
Yeah, I think I wrote it down. Thanks for that. It should just be TO here. Good catch. Sometimes when 90% of the formula is the same, you read the wrong lines.
It's also just be TA, right? It's not TA minus T.
Yeah. Everybody see those two corrections? Yeah, 'cause that's why you have this stuff in the denominator. That T is there, and then this one is from over here, right here. Okay, any questions? Yeah.
I'm a little confused on the top of the right board where it's UA, TA minus T. Why isn't that the derivative of that with respect to volume? When we derive it, everything else seems to be a derivative with respect to volume. And that's just Q dot, not EQ dot over
Yeah, I mean, this is the local TA, so this is still a function of the position in the reactor. This is still a function, but locally, it's not changing because when you think about it in terms of a differential, you're doing it over a small differential region. Remember the first thing I drew up there, right? So you're over a small enough space so that the temperatures aren't changing, so it doesn't end up being differential there. So I mean, but this is equal to dq dv. That's where we got that from. That is UA TA minus T. So where did we get that from? Well, you can go back to what is the total amount of heat over a total volume region, and that's equal to the same thing. And then we take the limit of this as dV goes to 0, and that's where you get the calculus version of that expression. But you can start with an energy balance over an annular region, and then if you take the limit of that energy balance as dV goes to 0, as delta V goes to 0, you get to the calculus version. Does that make sense?
It seems to me that on the second one, it should be divided by delta V. I don't know. Yeah.
No, the areas have different formulas.
Oh, okay.
Yeah, the areas are slightly differently defined. There's still a heat transfer area, but. Okay, so what would you expect for a PBR instead of a PFR? So what's going to change in this formula? I hope you guys got that far. It's a tubular reactor, right? So we're going to use a differential form. What changes up here? This is now a function of what? Instead of volume? Weight. Anything else change? This part also changes. Instead of just having a UA here, you have UA over rho B, which is the bulk density of your solid. And that's reflecting the fact that you have a solid, not a liquid, so you don't have perfect contact between the solid that's inside the reactor and the heat contact area. So I think that's the only difference. I'll just double check real quick. I mean, it factors in. It has an impact on your cross-sectional, on your overall heat transfer coefficient as well. But you're just going to be given this. Is the only difference. Is you'll be given that instead of just UA. And so just don't freak out when now there's a rho B in the problem statement. And in fact, that's the example we're going to do is a PBR.
What term is replaced with those two terms?
The UA.
Yeah. Oh, okay.
UA becomes UA over rho B.
And in a fluidized CSTR, the UA remains the same, or?
That's a good question. I have to look into
Okay.
it. I would assume that it would still be there as well. That rho B would be in the fluidized CSTR equation too. Yeah, that was kind of an afterthought in this book. There's 3 reactors, sometimes 4. Okay. A goes to 2B in a PBR with T naught equal to 450 Kelvin, and it's a gas phase reaction. It is irreversible. We're also given the heat capacity of A. Nope, sorry. We're given the initial concentration of A, 0.25 moles per liter. The initial flow rate, (5 moles per second). The initial pressure, and it says the cooling fluid mass flow rate is so high that TA is equal to 300 Kelvin constant. UA over rho B equal to 5 watts per